This video goes over the solutions to the AP Calculus AB quiz from Friday, January 30th. First page is the quiz, and the second page contains all the solutions to the quiz. You can find a link in the description that will take you to these two documents here. So question 1. Given this function on the closed interval from -4 to 0, is there a value for c in between -4 and 0 such that f of c, the output of f, is 4? If so, state the reason and find the value for c. So this problem is asking about the intermediate value theorem. We want to use that theorem to justify that this is or is not true, or if we can conclude. So f of c equals 4. We have to compare that with the outputs of f of -4 and f of 0, and this 4 has to be in between those outputs. Also, the function has to be continuous on the interval from -4 to 0 as well. Looking at this function, I know the domain of this function is -5 to 5, including those values. So there's no discontinuities in between -5 and 5 here, so this function is continuous on that interval. So it will be continuous on -4 to 0. And that's one of the two conditions that have to be met in order to find a value promised by the intermediate value theorem. So before I write that down about continuity, let me just check to see that this 4 is in between the y values of the endpoints. So f of -4 is equal to the square root of 25 minus 16. That's equal to the square root of 9, which is 3. F of 0, input 0 for x here. We have the square root of 25, which equals 5. So sure enough, f of c equals 4 is between 3 and 5. That's one of the two conditions that have to be met in order for the IVT to hold. The second condition is that this function is continuous on the interval. So I'm going to state that f is continuous on the closed interval from -5 to 5. I want the reader to know that I know the function is continuous on all those values there. Therefore, f must be continuous on the interval from -4 to 0, because that's within the interval from -5 to 5. So even though the problem doesn't talk about the intermediate value theorem, we have to recognize that in the question. And these are the two conditions that have to be met. Therefore, the intermediate value theorem holds true. So by the intermediate value theorem, there exists some number c that's an element of the standard interval of the interval from -4 to 0 such that f of c equals 4. So we just stated the reason why there must exist a value, and now we need to find that value. So the output is 4. We're trying to find what is that value. So the equation is 25 minus, I'll go ahead and put c. C is our input here, c squared. I square both sides. This equation, we get 16 equals 25 minus c squared. Now I'll go ahead and add c squared to both sides of the equation, and then subtract 16, and we get c squared equals 9. 25 minus 16 is 9. Take the square root of both sides. Both plus and minus 3 plus and -3 squared will output 9. Now, these solutions have to be in the interval from -4 to 0. That's what we're promised by the intermediate value theorem. So 3 is outside of that interval, so the only solution will be -3. Question 2. So the problem tells us that the third derivative of an equation y with respect to x will be 2. And then they tell us there's a negative 1 comma 3 is a point of inflection at which the slope of the tangent line at that point of inflection is 4. Find the equation of the curve. So we want to figure out what y is equal to. Now, this part here, negative 1 comma 3 in blue, that is a point on the curve of y. So we're going to use that at the very end. This implies if we plug in negative 1 into our function or equation with y, we plug negative 1 for x, we're going to get out 3. Now it says there's a point of inflection at that point. To be an x coordinate or to be a point of inflection, the second derivative must equal 0 when you input that x coordinate. That's one of the things that must be true. Sure, the second derivative also has to change signs at that value for x, but for this problem right here, we just need to know that the second derivative of y with respect to x, if we use the point negative 1 comma 3, has to equal 0 if there's a point of inflection at this point. Now it says the slope of the inflectional tangent. So there's a tangent line at this point of inflection, negative 1 comma 3, and that slope is 4. So that's telling us dy dx. That'll give us the slope of the tangent lines of y at the point negative 1 comma 3 is going to be 4. So all this information is packed into this question here. And the end game is to solve for y. So I'm not going to show the integral, but I'm going to take the antiderivative of the left side, the second derivative, or sorry, this is the third derivative right here. So if I take the antiderivative of this third derivative, we get the second derivative. That'll be the second derivative of y with respect to x. And I'm going to take the antiderivative of 2 with respect to x, and that becomes 2x plus my constant c. Now, because there's a point of inflection at negative 1 comma 3, when you plug in negative 1 and 3 for x and y, I only have x here though. If you plug in negative 1 for x, the output should be 0. So I'm plugging 0 in for the second derivative of y with respect to x. I'm plugging negative 1 in for x. This is negative 2 here. Add 2 to both sides, you get c equals 2. All right, so now I'm going to just rewrite the second derivative, but I'll replace this c right here with the number 2. Now if we take the antiderivative again, the antiderivative of the second derivative will just be the first derivative of y with respect to x. I'll take the antiderivative of the right-hand side. That's x squared plus 2x plus, just so there's no confusion, this is some new constant now. I'm not going to call it c, just so we're not confused. That's some new letter, we'll call it, or new number, we'll call it b. Now it says here, the slope of the tangent line at the point negative 1, 3 is 4. So I'm going to plug in 4 for dy dx and negative 1 in for x. So I'm using this information right here. 4 equals, so 1 minus 2 is negative 1 plus b. So b is equal to 5. Okay, I'll come up here now. So this equation here is the first derivative of y. I'm going to take the antiderivative of both sides with respect to x. So the antiderivative of the first derivative will be y equals. Now I should plug in 5 right here for b and maybe rewrite the equation, but we'll go ahead and just take it from here. So I add 1 to this exponent. So I'm taking the antiderivative divided by that exponent. It's the power rule. Plus x squared. So the derivative of x squared is 2x. That checks out. Now this should be a 5 right here. The antiderivative of 5 with respect to x is 5x. Now I need another constant. I'll go ahead and put plus a. Now this is going back to the original problem that negative 1 comma 3 is a point on the graph, on the curve, where there's a point of inflection. And so I'm going to plug in 3 for y and negative 1 in for x. All right, so negative 1 in for x here, and 3 in for y. Now I'm going to go ahead and solve for a. So we get 3 equals negative 1/3 plus 1 minus 5 plus a. 1 minus 5 is negative 4. Add 4 to both sides, we get 7. I'm going to go ahead and add 1/3 to both sides. So this plus 1/3 came from adding 1/3 to both sides. That 7 is because 1 minus 5 is negative 4. I added 4 to both sides of the equation. That became a 7. If I create a common denominator here, 7 is the same number as 21 over 3. So 21 over 3 plus 1/3 is 22 over 3. That's equal to a. So the last thing to do is just to rewrite this equation. That was our goal, was to find the equation of the curve. If you plug in right here, x is negative 1 and 3 for y, you're going to get a true statement. All right, so this is our solution to that question. Question 3. It says to use separation of variables to find capital G of t. And they want us to find the particular solution, and the differential equation is given, and the initial condition is also given. So this is a very common question on the College Board exam, typically on the free response exam for calc. So what we want to do is we want to separate the variables where we have dt in the numerator. Right now dt is in the denominator. And we want to get the capital G, the terms with capital G, on the same side of the equation, and lowercase t on the other side. So I'm going to divide, this is capital G minus 2 as a factor, so I'm going to divide both sides by that factor, and also I'll multiply both sides by dt. Okay, so multiply by dt here. I just separated the variables. And usually on the free response exam for the College Board, that's a point, just for separating that correctly. Now I need to take the antiderivative of both sides. The antiderivative of 1 over g minus t with respect to g is the natural log of the absolute value of g minus 2. The antiderivative of 2t squared is t squared. The antiderivative of 3 is 3t, plus some constant. Now, that right there on the College Board exam could be 1 or 2 points, depending if they give you a point for the left side and right side, or maybe just 1 point combined. But just check my work. The derivative of this logarithm is 1 over capital G minus 2 times, I'm using the chain rule, times the derivative of g minus 2, which is 1. Sometimes the College Board will put 2 minus g, which then if you did the chain rule, you'd have to multiply by negative 1, so you'd have to have a negative over here to make this a true statement if you took the derivative of this. But this checks out. Now, it's in this step right here where that's my preference. When to find c is right here in this step. So I'm going to plug in 0 for t and negative 4 for g. So I took this 0, plugged in for t, and negative 4 in for g. So natural log of absolute value of, it's going to be negative 6, absolute value of negative 6. And the absolute value of negative 6 will be 6. 0 squared plus 0 plus c. Now I'm going to go ahead and rewrite the equation. And plug in natural log of 6 for c. All right, now the last step is just to solve for y. So finding the constant of integration is usually worth a point on the College Board exam as well. Right here, it'll be worth a point if we solve this correctly. I'm going to take base e of both sides because e is the inverse of natural log. So we get absolute value of g minus 2 equals e to the power of t squared plus 3t plus natural log of 6. So I take base e of both sides, and I can see natural log and e are inverses, but I'm going to take a step to rewrite that in just a moment. Now, the initial condition is g of 0 equals negative 4. 0, comma, negative 4. When you have absolute values here, the solution to this differential equation has to be a function and it has to be continuous. So we're going to go ahead and decide, will this y value make what's inside the absolute value of this argument, will it always make it positive or negative? What condition do we have here? If we plug in negative 4 here, we have negative 4 minus 2 is negative 6. So that means I have to take the opposite. Oops. I have to take the opposite of this argument. Why? Because when you plug in negative 4 here, you have the absolute value of negative 4. And if I remove the absolute values and write negative 4, that would not be a true statement. The absolute values makes that negative 4, it makes the output become positive 4. I have to take the opposite of that input. I showed my students how to rewrite this as a piecewise function using the definition of absolute value. And then you have, if you're always plugging numbers for g less than 2 for this particular solution, negative 4 is less than 2. You plug in a number in here less than 2, this argument inside the absolute values will always be negative. So when we remove the absolute values, we have to take the opposite here. If this number was bigger than 2, then that number bigger than 2 minus 2 would be positive, and so you remove the absolute values and just keep capital G minus 2. So you must make a decision on which particular solution we have based on whether this output will make what's inside the absolute value positive or negative. Now over here, I'm just going to rewrite this as e to the t squared plus 3t times e to the natural log of 6. You know that when you multiply by this same base, you leave the base the same, and you add the exponents. So this would combine to the step above. Now, e to the natural log of 6, those are inverses, so that simplifies to 6. So in this step, I just showed you how this right here becomes a 6 there. Now my preference would just be to add g to both sides. So here I added g to both sides and I subtracted this term. And so we have capital G of t is equal to that. And that's our solution to this differential equation. Question 4. At what time is the particle changing directions? State the reason. So a particle changes directions when the velocity changes signs, when the velocity goes from positive to negative or vice versa. So you're given the velocity function. So I'm going to graph that. So this graph will represent the outputs of the velocity function. The zeros of this velocity function, it's in factored form, so I can see it's 0 and 3. But you have to be careful. The leading term would be negative t cubed. If you take t squared times 3, you get 3t squared. But t squared times negative t is negative t cubed. So the degree of this polynomial would be 3. But the end behavior on the right side, the graph is decreasing because the leading coefficient is negative. Because this power of 3 minus t is 1, because that multiplicity is odd, the graph's going to cross at 3. And then because this is t squared at this 0, because that multiplicity is even, that power is even, the graph's going to bounce off of that axis. So when the velocity is positive, I'll go ahead and right here in blue, the velocity is positive. Right here it's 0, so the particle stops, but then it continues moving to the right. From negative infinity to 3, the particle is moving to the right because the velocity is positive, or it stopped at 0. It didn't change directions there. And then from 3 to infinity, the velocity is negative, so the particle is moving to the left. So the particle is going to the right, and now it's going to the left. So the particle changes directions. This is part A. The particle changes directions at t equals 3 because the velocity changes signs. Okay, common wrong answers. Kids want to include 0, but if you're driving your car going in a direction, you stop. Just because you stop at a red light doesn't mean you're going to change directions. You'll continue on going in this case. All right, part B. At what times is the velocity of the particle decreasing? Well, state the reason. The reason is going to be if the velocity is decreasing, the acceleration is negative. So I could just see, though, look at the velocity function. The velocity is decreasing from negative infinity to 0, so I know that for sure. And the velocity function is increasing from 0 to, I currently don't know what this value is right here, but from 0 to this value, the velocity function is increasing. And then from this value for t all the way this way, the velocity is decreasing. So I'm going to have to figure out when the slope of this tangent line here is 0. That'll give us this t value, this relative max. And so I'm just going to go ahead and find the acceleration. So the velocity function was given. I think it'll be easiest if I just expand. I need to find acceleration, which is the derivative of velocity. So I could take the derivative and use the power, well, the product rule, to find this derivative, or I could just distribute the t squared to both terms and rewrite it like this. And now when we take the derivative of the velocity function, it'll be a little bit quicker. We get 6t minus 3t squared. So I'll factor out 3t and get 2 minus t. So this is a quadratic. The acceleration function is a quadratic function. The graph should be a parabola. Our zeros of this function are at 0 and 2. The leading coefficient is negative 3. So just like the other function, this graph will be decreasing as x is approaching infinity. And then it's going to cross at 2 and at 0. These multiplicities are both 1, plus it's a parabola. The graph is a parabola. So we can see the velocity is decreasing when the acceleration is negative, which is negative infinity to 0, union 2 to infinity. Looking at this graph here, we just figured out that this value here is 2. So the velocity function is decreasing from negative infinity to 0, union 2 to infinity. That's exactly what we have right here as well. So let's go ahead and state our solution here. The velocity is decreasing for values of t that are the element of the set of from negative infinity to 0, union 2 to infinity. Because the acceleration function is negative. You can write out in words acceleration function is negative, or v prime is negative. All right, part C. At what times is the speed of the particle increasing? The speed of the particle is increasing when the acceleration and velocity have the same sign, meaning when they're both positive, both negative. And that's when the speed will be increasing. So for part C, I'm going to look at the product actually of the acceleration and velocity function, because if they're both positive and a positive times a positive would output a positive, and if acceleration and velocity are the same sign and they're both negative, a negative times a negative would be positive. Now in the previous problem, we figured out the acceleration is right here, 3t times 2 minus t. So I'm going to replace a with 3t times 2 minus t. And then in the original problem, we're given the velocity is t squared times 3 minus t. I want to know, when will this be positive? Now, before I go and graph this polynomial, I see that I have t squared right here and t there. So t times t squared would be t cubed. So I'm going to rewrite this as 3t cubed times 2 minus t times 3 minus t. The zeros of this polynomial are 0, 2, and 3. The leading coefficient would be positive 3. So here we have 3t cubed times negative t, so that's negative 3t to the fourth, times negative t again would be positive 3t to the fifth. So the function will be increasing. As x approaches infinity, the graph will be increasing. And all these multiplicities here are odd, so the graph is going to cross and change signs at each of these zeros. So we're looking for when this product, when the acceleration and velocity are the same sign, so that product will be positive. So in blue is the part of the graph that is above the t-axis, and that's when the outputs will be positive. And the part in red is when the product, when the acceleration and velocity will have different signs, because that product would be negative, and that would be below the graph here in red. So the speed is increasing. For values of t, element of the interval from 0 to 2, union 3 to infinity. Because the acceleration and velocity functions have the same sign on that given interval, or for those given values. All right, this is another way to look at it, which is pretty cool, is I'm going to go ahead and take this velocity function here and draw the graph here. Now speed is equal to the absolute value of the velocity function. So this graph here, the velocity function graph, is not going to change by much. The part in blue is going to stay just like it is. But this part in red, since we're taking the absolute value of the outputs that are negative are now going to become positive. And so if you look at this speed function, where is the speed increasing? Right here at 0, it's increasing all the way up to 2, 0 to 2. And then from 2 to 3, the speed function is decreasing. And then from 3 to infinity, the speed function is increasing. Question 5. It says a region is bounded by the curves y equals x cubed, x equals 0, and y equals 8. So here's y equals x cubed. The y-axis is x equals 0. We'll call y equals 8 up here. And this is the region in pink that's bounded by those curves. Now it says set up but do not evaluate an expression to find the volume that's created by revolving this region about the y-axis. So if we revolve this region about the y-axis, we're going to have to find the volume of this solid. So I'm going to draw cross section up here at the top, one more here, another one here. So we're going to find the sum of all these cross sections from 0 all the way up to 8. And the thickness of these cross sections is dy. It's like the height. They're super thin of each cross section. Now, I want to find the radius of each cross section. So all the way across here is diameter, diameter. So that's the diameter of a cross section in red. So I want to find the radius of this diameter, or of this circle here, by finding this value. So this is x equals 0, and we're going to go to the right. I'll go ahead and draw one of these cross sections here. So this is x equals 0. And then how far to the right am I going from x equals 0? So what is this value for x? Well, I have to use this equation, y equals x cubed. But I want to know the value for x. So I'm going to take the cube root of both sides. So the cube root of y equals x. Or I can say x, the value for x, so how far am I going to the right, is equal to the cube root of y. And that'll be our radius. So the area of a circle is pi r squared. The radius is the cube root of y squared. And then we're going to find the volume of this cross section, which is a cylinder. So it's pi r squared times the height, or its thickness, which is dy. Now that is the equation, or the expression, that would need to be evaluated to figure out the volume of that solid. All right, part B. We're going to take the same graph, but we're going to revolve it about the line x equals 2. So x equals 2. I got to know where x equals 2 is at. Now, I realize that if I plug in 2 for x here, 2 cubed equals 8. So this point right here is 2, 8. That means the vertical line x equals 2 is right here. We're going to revolve this solid around that line x equals 2. And we're going to take the volume of, if I take this cross section all the way across here, all the way across, this is just going to make a right cylinder. And we're going to find that volume, and then we have to deduct this part in the middle that's hollow. We have to subtract all of these cross sections. That's how we're going to do this problem here. So this is part B. It's very similar to the last problem. We're going to take all the cross sections from 0 all the way up to 8. I'm going to go ahead and do one integral. You could do 2 separate integrals if you want to. It's going to be pi r squared times the thickness. Pi r squared is the area of the circle times the height. So this blue cross section, if I draw a radius from here to here, I can see that value will just be 2. It's always going to the vertical line x equals 2. If I go all the way across, that's a distance of 4. All the way across here is distance of 4. So every one of these blue cross sections has a radius of 2. We're finding the volume of this cylinder. We're going to deduct the middle part. So pi r squared, so it's going to be 2 squared. And then we're going to subtract the area, or I should say the volume, of the middle part. So I have to find, I'm going to erase some of this here so it doesn't look so messy. All right, so I need to subtract the volume of this part here. Now, the radius of each of these cross sections, So if I were to draw a sample one here, I want to find this radius. So from the y-axis to my fingertip here, this is the radius, which is currently fingertip to fingertip is 2 units. But I have to take away this amount here to get the leftover radius. So again, this is a distance of 2. This is x equals 0. This is x equals 2. That's a distance of 2. My radius is this little piece here. So I have to subtract this amount. And we already figured out what this amount is in the last problem. We're going to the right. X equals the cube root of y. So I have to take 2 minus the cube root of y gives us the leftover. 2 minus the cube root of y. So the radius of these cross sections in here is 2 minus the cube root of y. And I have this squared because, well, to find the volume of the cylinder, it's pi r squared times the thickness. You could create 2 separate integrals if you'd like. Okay, question 6, part A. You have to recognize that this integrand here, when we take the antiderivative of this, we're going to get the arc sine function. We're going to get arc sine of x. Maybe you recognize that if you take the derivative of arc sine of x, you get this expression here. And we're going to evaluate this for values 1/2 and 1. So this is equal to the arc sine of 1 minus the arc sine of 1/2. So this is just a review of pre-calc right here. When I look at arc sine of 1, I know arc sine inverse trig functions output angles. And now sine is going to represent this 1 here. So that's the sine. That represents a y-coordinate unit circle, which is right here, 0, 1. So the arc sine of 1 will be that angle pi over 2. Just a little bit of review, but the arc sine has to output angles in between or including negative pi over 2 up to pi over 2. Arc sine of 1/2. So again, arc sine has to output an angle. Since this is sine, this 1/2 right here represents a y-coordinate on the unit circle, and we're familiar with that value. This point here is the square root of 3 over 2, comma 1/2. Now this angle is pi over 6. So we take away pi over 6 from pi over 2, and we're left with pi over 3. That's our solution. Part B. We're just taking the antiderivative of these 2 trig functions, so we need to know these formulas here. We get the natural log of the absolute value of secant of x, plus tangent x. So the antiderivative of secant of x is natural log of secant of x plus tangent of x. Let me highlight that. And now we need to take the antiderivative of, I'll put a plus here, I don't have enough room, the antiderivative of tangent of x, which is the natural log of secant of x plus our constant. All right. Part C. We're going to take the derivative of the arc secant of 4x. So we're hopefully familiar with this formula. It's 1 over the argument 4x times the square root of 4x squared is 16x squared minus 1. Now we have to use the chain rule. Times the derivative of 4x will be times 4. So those 4's are going to cancel, and you get 1 over the square root of 16 x squared minus 1. Part D, the antiderivative of cosecant of x dx. It's another one of those we learned this past week that we have to know. This is the natural log of cosecant of x minus cotangent of x plus c. Part E, the antiderivative of 1 over x squared plus 9 with respect to x. So we have to look at this and realize, hey, this looks a lot like the antiderivative of 1 over x squared plus 1, which would output the arc tangent of x plus c. If you try to let u equal x squared plus 9, you would get stuck. So you need to recognize this as being very similar to this integrand here. The only problem is we want a 1, and there's currently a 9 there. So we're going to factor out 9 from the denominator. And we'll get x squared over 9 plus 1. Let's check that. 9 times x squared over 9, the 9's will cancel, you get x squared. 9 times 1 is 9, perfect. So I'm going to rewrite this as 1/9 outside of the integral. Now, this 9 was bugging, it's a 1 there. Now we have x squared over 9, which isn't the same as x squared, but that's okay. We could use deductive reasoning here and just put what we think our solution is and take the derivative and check it, or we can use u substitution. We can let u squared equal x squared over 9. So I'm letting x squared over 9 this here. If it's u squared, then my antiderivative would be arctangent of u. That'd be nice. So now I'm going to take the square root of both sides, and that's u equals x over 3. Now I'm going to take the derivative of both sides of the equation with respect to x. So that's du dx equals 1/3. I'll multiply both sides by 3. That's 3 du. Multiply both sides by dx. That's 1 dx. So now here we go. I'm going to go here. So I have this 1/9 right here. I still have the integral. 1 over. We let x squared over 9 be equal to u squared, so that's u squared there. We have this plus 1. Now right here, dx. dx has to be replaced with 3 times du. All right, this 3 and 1/9. I'm going to go ahead and write that as 1/3. The integral of 1 over u squared plus 1 du. Now this is just like what I have up here, except instead of x, I have the letter u. So this will be 1/3 arctangent of u plus c. Now I must replace u with x over 3. And that is our solution. All right, the last problem. Part F. All right, so this says evaluate f prime of 3 given this function here. So the first thing I want to see before I do anything is this function continuous at 3? I'm trying to find f prime of 3. If this function is not continuous at 3, then it will not be differentiable. That was the problem from the previous quiz. The problem wasn't continuous at that value, therefore it was not differentiable. So the limit as x approaches 3 from the right of this function would be 3 squared, which is 9. The limit as x approaches 3 from the left of this function, plug in 3 here, you get 18 minus 9 is 9. So when you plug in 3 here and there, the limit from both sides will be 9, which means there's not essential jump discontinuity. The piecewise function actually comes together at this point, 3, 9. So the function is continuous. Therefore, there could be a derivative. So that's our next thing, is let's check f prime of x from the left side of 3. So here's the left of 3. The derivative of 6x minus 9 is 6. And there's nothing to plug in. It's just a constant. The slope of this line is always 6. Now, f prime of 3 from the right side. The derivative of x squared is 2x. Plug in 3, input 3, you get 6. So this function is continuous at 3. And we just showed the left side and right side derivatives are equal. This implies that f prime of 3 equals 6. All right, I hope you found this video helpful.